Hello, all. I'm going to be giving a fairly short, hopefully you can see this. Can you see the full screen now?
Perfect. Yep.
Awesome. So I'm going to just give a brief summary of the most important points in section 1.2 of the IBM Qiskit textbook. For most of our lectures going forward, the past ones were kind of like introduction to quantum and then set up a quantum computing development environment. But going forward, we're going to mainly be going quite parallel to the Qiskit textbook, just because it's an absolutely incredible resource that IBM provided the community with. And so this is going to be going over yes, the atoms of computation, but also towards the end, how to build your own or your first quantum computing circuit. So before we talk about quantum computing, it's imperative that we actually talk about classical computing first, or digital computing, because it's very much quantum computing has been built in response to the needs, the lack of ability that has been displayed in classical computing architectures. So binary is the world's simplest alphabet. This is what our computers use to perform operations, simply because it's really easy to physically represent. You know, when you're representing electrical pulses or signals, you can't really represent an electrical pulse as some string of letters or some image. That would be very hard. You have to actually bring it down to this world's simplest alphabet of bits, right? And so we've got this idea of encoding information into our binary. And when I say binary in bits, a bit is just a binary digit, and so that's a 1 or a 0. And binary is the encode, or not the encoding scheme, but the base, right? Because it's base 2, as opposed to base 10, which is what we commonly use. But before we talk about base 2 and base 10, it's important to just go over the fact that we do at some point have to move over our books and our images and our games into bits, and we do that through encoding schemes that are standardized, like UTF-8, 2's complement for floating numbers, floating point numbers, floating numbers. But this idea allows us to kind of have some standardized way of creating information or moving information from what is easily accessible to us to something that's easily accessible to computers, right? And so we have this idea of the base 10 number system, and that's very familiar to all of us because we count to 10 on our fingers and then we start over. Of course, we add another digit on the left hand side, or wherever it is that this digit is, to continue counting in the base of 10, right? And so if we were decompose this number 120, we would decompose it into 1 times 10 to the third power plus 2 times 10 to the second power plus 0 times 10 to the first power, because 1 times 10 to the third power is 100 and 2 times 10 to the second power is 20. So you add those together plus some 0 term and you get 120. And that's the way that we construct base 10 numbers past just 10, right? And if we were to take that same number and we move it over to binary, this is what it would look like: 1 1 1 1 0 0 0. And the reason for that is because we break it down in very much the same way, except instead of doing the base of that exponential term as 10, we actually do it as a base 2. And so again, we do 1 times 2 to the 7th plus 1 times 2 to the 6th plus 1 times 2 to the 5th, et cetera, et cetera, et cetera, right? And we get the same number overall, but we have used a different base to represent it, right? And so this is the foundation of binary representation, and it gives us kind of some insight into the way that we construct integers with binary, right? And so now we can talk a little about representing computing, representing the operations that take place within a computer as diagrams. just because like pictures are fun and super helpful when we're learning new things, right? This right here is like a diagram of a classical or from a classical computing framework. We're not going to talk about like what specifically these gates are, but like the highlight is you read from left to right, just like you read in a book, right? And these like one thing that I would note that is important is that like when you see these bifurcations, this is the same signal, right? Like we can think of these as electrical signals that are going through these like signal manipulators, right? And so these signal manipulators, they like, combine them, they do funky things that allow us to perform logical operations, right? Like and or not or nor, et cetera, et cetera, et cetera. But these bifurcations is just a replication of the signal. And this is something that you'll see a lot because we don't always just like get one input and just send it straight through to the right. You know, there's a lot of times that like we actually need to interact with this input more than once. And so this bifurcation allows us to do just that. And then we read the outputs on the rights.
And do you mind if I talk?
Yeah, go for it.
Yeah, I was just gonna say, it's also like a big difference in quantum computing. Bifurcation like that is very tricky to do. It's very hard to just copy quantum states because there's so much. It's so sensitive to interference compared to classical computing, where interference is almost never a problem. And it just goes to show you just the major differences in classical gate logic versus quantum gate logic. But yeah, anyway.
Certainly. So like, and that leads us to like, well, how about the quantum gates, right? This is something that like is actually representative of the gate that we're going to build in a second. This is a half adder gate, and it's not super important right now what this all does individually as each part. But some things I will highlight are that these over here, these lines going horizontally are representative of the qubit, of each individual qubit, right? And so we like, this is a 4-qubit system. We initialize 4 qubits, qubit 0, qubit 1, qubit 2, qubit 3, right? And that allows us to begin performing operations on these qubits. And like Will said, it's hard to copy information. In fact, it's impossible to just directly copy information. You can transfer it, but it's impossible to directly copy it. There's a no cloning theorem that's like extremely, extremely important, but we won't go into it because that's for another day. But we have this idea of like, we're still reading from left to right, and we've got qubits right here on each line. And this over here is representative of a measurement. So you see this, and this is kind of like, all right, that's the end, or at least that's the end of the knowledge that we can get out of qubit 2 and qubit 3, right? Qubit 0 and qubit 1 certainly have some aspect to them that like maintains their properties if they're not operated around on. But once you measure a qubit, you're collapsing the state. So measuring qubit 2 and 3 is collapsing both of those states. And so maybe another thing that I'll quickly highlight is the barriers. So these right here, it's really just to give our mind a little bit of a, hey, like move on to the next stanza or next paragraph, right? Simply because having a bunch of jumbled operations or diagrammatic representations of operations is kind of like lots for brain. I'll go on to an example circuit to just illustrate something like very quick and dirty before we move on into something a little more interesting. So this is very literally just initializing and measuring. And this is actually like, as trivial as it may seem, it's helpful because it illustrates something that like needs to be illustrated. And that is that when initializing all of these qubits and then measuring them, having done no operation on them, this is the output. You are getting an output. So like, interesting thing here is that when we get this output, it will be measured as a composition of all of our qubits, right? Because we throw them all into the same like measuring apparatus, right? And so we've got 8 qubits here, right? And we also have 8 digits down here. And if you notice, we have 100% probability of getting 8 zeros. Every time we will get 8 zeros because Well, we initialize them and they start at 0. So that's good. We've learned something right there. Every time you initialize a qubit, the default state or the default value is 0, which is good to note because it's just important information going forward. Something that I might like highlight just because like, why did I put a diagram representing probabilities? When you run the circuit, it's not really like a digital computer where you run it and then, okay, let's see, what did my computer print out? You actually, because it's probabilistic, we run it like hundreds of thousands of times, maybe not hundreds of thousands, but like quite a few times so that we can get some distribution of what our probability looks like. And so looking at results, you're not really looking for like, oh, it printed the value of 7. No, like it might print the value of 7 one time, but it might also print 472 another time. And so what you actually do when you design a circuit is you do shots is what they call them of the circuit, and you shoot like information through these circuits multiple times so you can get a distribution that gives you some information about what it looks like on average, right? Or like whatever it is. But this, as you can see, is just illustrative of the fact that we initialize a qubit and it's initialized to 0. Now we're gonna do something a little more interesting. We're going to try and simulate addition on a quantum computer, and this is a little more difficult, but it's something that's like it's useful, and like we can't really have a very practically useful computer without being able to do addition, right? And so there's of course more in-depth explanations as to like how and why this works, but I'll sum it up into this. There really are 4 cases when we're adding 2 bits, right? And so like 2 bits, we got 2 possibilities for each bit, right? They can each either be 1 or 0. And so when we add 1 or 0, we end up getting either we can add 0 and 0, which in this case, it's just 0. We can add 0 and 1, and it will be 0, 1, or 1, right? As illustrated there. We can also add a 1 and 0, and again, it's just going to be 1. Or the really funky case is we add 1 and 1. And then it's kind of unintuitive because it's like, well, you've got 2, but wait, you can't have 2s, you can have 1s or 0s. But just like the same way we do it in base 10 arithmetic, where we carry over the digit that kind of like overflows base 10 onto the like the left sum, that same thing is done here. And so we will carry over, upon adding 1 and 1 getting 2, we'll carry over that 2 and we'll put it over here because this is 2 to the 2, whereas this is 2 to the 1. And so like implicitly it retains the same value as 2, right? Because it's base 10. So those are the 4 cases, and we need to figure out how to address them with quantum gates. So these are the gates that we're going to need. First, we've got the NOT gate, which the NOT gate, very simply, just like the digital computing NOT gates, they just they invert the bit. So if it's a 0, it's now going to be a 1. And if it's a 1, it's now going to be a 0. Very simple. Now we have conditional knots or C knots. What this does is you've got 2 bits. You've got a control and a target, right? And so your control is determining the operation that you're doing on the target, right? And so we will look at the control and we will say, is this a 0? If it's a 0, then we won't do anything to the target bit. If it's a 1, we're going to do a NOT to the target bit, right? So it's a conditional NOT. It's very simple. And so like it is equivalent to an exclusive OR, right? Where an exclusive OR is kind of like, give me 1, not both. And if there's only 1 and not both, then it's cool. But if there's both, then like, don't want it, right? And so if input A is 1, then input B, having been 1, will be 0. And we will get some like evaluation of a false because it's exclusively ORing those 2 bits, right? Toffoli is just like that, but it's extended to 2 control bits, right? So the same concept, like, okay, if the control is 1, we do a not. Except if both controls are 1, then we do a not, right? And that's the idea behind Toffoli. It's just an extension of the conditional not. So like we need to like break this down into a problem that's like a little easier to chew, right? We've got the left bit and the right bit that we need to worry about, right? Because we're only adding 2 bits, so we can only get a value that is equal to the sum must be equal to 2 bits, right? It can't really be like 3 bits unless you're adding like leading zeros, but we wouldn't do that, or it's not relevant. We should first talk about the rightmost bit, right? And so like to talk about the rightmost bit, like we can see that the rightmost bit is going to be 1 in these middle 2 cases, right? And what you can actually see is, which is interesting, is that whenever the actual not factors, but the 2 terms in the addition are the same, we won't have that being a 1. So when the 2 terms are the same, when it's 0, 0 and 1, 1, it'll be a 0. So that gives us some really interesting information, and it's kind of like, whoa, wait, didn't we say XOR does something like that? And it does. And the way that we'll accomplish something like that, if we look at just like the output of an XOR gate, we can see, well, 0, 0, it's 0, 0, 1, it's 1, and 1, 0, it's 1. Awesome. That's it. 1, 1, it was 0. Like it accomplishes the exact same thing, right? And so this is the gate. It's going to be a not on the 0th qubit, because and the reason the not is here, the not is not part of the operation. The not is actually the encoding of our information, of our actual terms in the addition. So what we want to do is we want to add 1 and 0, right? And so we are going to say, okay, qubit 0 is 1, qubit 1 is 0. And because they're initialized to 0, like we couldn't ever add anything but 0, 0 unless we threw in nots, right? Because we saw like right here, if we were to just initialize and start adding, like we would just get 0, because like you add 0 and 0 and like what, not very helpful, right? So we need to initialize our actual data, and we do that by doing a not. And so what this is saying, it's saying let's add 1 and 0. And the way that we're going to determine the rightmost bit is we're going to do this conditional not, right? Which accomplishes the same thing as XOR. And so this conditional not is allowing us to determine, okay, we want an output where it's 0, 1 if they're different, or it's 0, 0, right? And so in the output, this measured output, you'll see it's going to evaluate 1 plus 0 is going to evaluate to 0, 1, or 1, right? 1 plus 0 is 1. That's awesome. And so like the thing to note though is we can't really like we can't just start going on to like, oh well, now let's determine the left qubit and kind of applying gates to those same things, because if we keep on applying gates before measuring, we're like overriding our rightmost bit. And so we're making things overcomplicated, and we need to introduce this idea of an ancillary qubit. And I didn't write it here, but it's something that you'll see in the literature a lot, an ancillary qubit. And the purpose of this is like this qubit that you use kind of like an extra piece of paper, an extra piece of scratch paper, right? You use it to like move stuff around and be clever with your operations to avoid doing things like overriding your bits, right? And so you'll see here we introduced two more qubits and another gate. And we're initializing both of these to 1. We're introducing another conditional not, which if we were to do this would just overwrite the information. Not super helpful, right? So what we need to do instead is we need to introduce a Toffoli, because the left only changes. Let's check this out. The left only changes when these are both 1. Now that's interesting because we talked about Toffoli and we said, oh, it's just like a conditional not except there's two controls. And so if there's two values, two qubits that are equal to 1, then it will do a not on the other qubit. And so that's really interesting, because if we say, oh, what if that qubit that is going to have a not be done on it is the leftmost bit in our sum, right? And so that's exactly what we're going to do. We're going to add this Toffoli gate over onto the first two qubits, and we're going to say, if these are both 1, then let's change this to 1. And so you'll see that we have 1 and 1 encoded here. We've got these barriers just to make it a little easier for us to look at. And then once we figure out the rightmost bit, we also figure out the leftmost bit by having this Toffoli gate measure onto this qubit 3, right? Which is measured, and it has a 1, 0. And this is always confusing for me, because it's kind of like it seems convention to like measure like this so that you're measuring top qubits before the bottom qubits, and then you end up seeing that like, oh, it's 0 and 1, but like that's like, it's 1, 0 here, like that doesn't make sense. But like, it's just kind of like, it's weird, it's flipped. So like, this would be the leftmost and this would be the rightmost. And so we see we've got leftmost is 1, rightmost, which is just the second one, that second ancillary qubit that we introduced, is 0. And so that at that point we get this nice half adder that allows us to add and actually get an accurate addition for 2 bits, right? And that's like where I want to leave it. But before we completely finish, I just want to make the note that like, this is not the complete solution, right? This is a half adder. And so while this can only chain bits together, there's still the extra overhead of like, okay, well, how do you chain these together? And we haven't done that yet, but next week we're going to work on actually implementing this. We're going to work on looking at the code that allows us to do this, and we're going to get our hands dirty building this, and possibly move on to, okay, great, like we figured this out, what's the next step?
Next
And
step
so
would
this,
be an ALU, right?
yeah, that
would be
some analog of that
yeah.
would be
No, building an entire ALU from quantum. I mean, it's gonna be done, and like, but like,
Yeah.
it is crazy.
Yeah.
I'm sure you can
So-
find an online version of that. Yeah. But thank you so much, Teddy.
Hell yeah, yeah.
All right. Is that it?
That is it.
All right. I'll pause it.
That's all I got.